Hello everyone, I'm Abir Mohammad Hadi from South Dakota State University, and I'll be presenting our work on task-dependent model complexity, shallow versus deep network. Deeper network models have opened a world unknown to many before. With the help of deeper networks, high-dimensional data problems are solved. The need for compact networks is growing as the end devices are still trying to harness the computational power in a small form factor, which is really important for our green technologies. Deeper networks come with immense power, but a vast amount of it remains unused for simple problems. A CNN learns the feature scale implicitly by image subsampling and correlating feature points from neighboring pixels using the kernels or filters. The constraints provided using the dataset are the bounds of the features that a network will learn during the backpropagation. Thus, the importance of a good and balanced dataset is crucial in success of this experiment. Let's take a look at what scale dependency means. Let's say we have an object represented in different scales, and each of the scaled object can be in different image. What we try to do in this experiment is that to learn a fixed scale object. So we fixed a scale of object and made it in the positive class, and all the other objects, whether it's smaller or larger, was in the negative class. For this, background features are mutually inclusive in both the positive and negative class, because in both cases only visual difference is the size of the features, and the rest of the parameters, for example relative location, shape, and color, are similar. Enforcing scale dependency thus turned out to be harder because of this issue. CNN filters are unaware of the location of a feature. It only focuses on number of similar features because of its pooling layer. This leads to arbitrary feature learning to minimize the loss and achieve the empirical objective. So network compression is a technique to get rid of the redundant filters or weights. Pruning is not straightforward and has severe implication towards the performance and success of a network. Unstructured pruning turns off redundant kernels globally to reduce computational cost during inference. Deeper networks suffer from aggressive pruning depending on the task they are employed to solve. Shallow networks should perform comparatively better given that they are trained correctly. For the experiment, as a baseline model, we chose VGG16 style network and a shallow network with 5 convolutional layers and a fully connected layer as a classifier. For the dataset, we built a custom scaled cars dataset from Kitty Cityscape and Stanford cars dataset. And the samples are distributed in positive and negative class, so it's a binary classification problem. The input size of the network is 80 by 80 pixel, and for the samples we have over 21,000 training samples, and for test samples we have over 5,300 testing samples equally distributed in positive and negative classes. Let's take a look at orthogonality and how our orthogonal regularizer works. So orthogonality among adjacent layers are enforced by generating orthonormal basis vectors, and during the training time we enforce the orthogonalization of the layers using this regularizing term, which we average layer wise, and we have a hyperparameter lambda that controls the speed of this update. In the result section, first let's take a look at the VG16 pruning result. In table 1, we show the accuracy of VG16 with pruning on scale-dependent dataset without orthogonalization. As we can see, as the pruning factor increased, the accuracy on positive class decreased. In table 2, we can see the similar result, but we can see with orthogonalization, with 60% pruning, the network performed relatively better than without orthogonalization. For scale-independent tasks, VG16 performed quite good without orthogonalization, but with orthogonalization, it performed a lot worse than without orthogonalization. That's because if we use orthogonalization, the network's filters learn explicit features that is recognized by the filters, and they do not share filters in the same layer. So because of that, when we prune, the networks that do not grow much is pruned off as we aggressively prune the network parameters. Here we can see the accuracy versus network parameter versus accuracy graph, and we can see how reducing network parameter affects the accuracy in VGG16 model. So for shallow network, we did not use any pruning because the trainable parameters are already reduced from the VGG16 model by the factor of 119. So the table 5 shows the accuracy of shallow model on scale-dependent dataset without orthogonalization, and table 6 shows the accuracy of shallow network on scale-dependent dataset with orthogonalization. We can see that with orthogonalization, in scale-dependent tasks, the network performs slightly better than without orthogonalization in the negative class. For the scale invariant task for shallow network, in table 7, we can see the accuracy of the shallow network on scale independent dataset without orthogonalization. Here you can see in the negative class, it performs far worse than the other models. In table 8, we can see with orthogonalization, we can achieve good result in negative class using the shallow network. So there is a question, why does pruning break the model? So in our dataset, the amount of mutually inclusive features were far too high because of the background features and also the scale features. So to reduce the empirical loss, the network does learn small but distinct discriminative feature of the samples, which introduces randomness in feature selection. This margin of randomness is narrower than a scale invariant model. This is why when the scale-dependent model is pruned too far, the discriminative filters are lost or turned off. Since the negative class has a data bias that utilizes the background samples, the broken network weighs more in the direction of negative class than that of the positive class, as the discriminative features required to predict the positive classes are lost. In this study, we showed the need to explore the need of task-dependent optical network architecture and the need for orthogonality in the shallower networks to perform on par with the deeper networks. We also showed that unstructured compression can break a network depending on the task the network is solving, since filters responsible for recognizing a feature can have lower rank compared to other filters. In future, we'll conduct experiments on varying size and class of dataset with different compression and initialization strategies to explore the nature the filters at different level grows, and whether we can initialize a better set of filters that will be robust to compression, yet perform as close as the deeper counterparts. Thank you so much for listening.